Hi, so welcome to the second part of the S2 chapter 2, the Poisson distribution. So yesterday we covered up to the approximation of binomial distribution through the Poisson distribution. So now we will look at the approximation. So approximation of Poisson distribution as a normal distribution. So yesterday when we look at approximating the Poisson distribution approximating the binomial distribution with the Poisson distribution, because both are discrete random variables or discrete probability distribution. So you don't really need to use continuity correction when you do the approximation. But now when you try to approximate Poisson distribution by using normal distribution, one is discrete, another one is continuous. So you need to do the continuity correction, and the procedure is exactly the same as how you would do it with the binomial distribution to normal distribution. So the point here is that you want to approximate Poisson distribution, which is only having one parameter, to the normal distribution. So in our previous discussion, we already mentioned that for the Poisson distribution, the mean and the variance are the same. So when you approximate from Poisson to normal, so you would expect that the parameters will be lambda, lambda. So this is normal. So one thing that you need to take note is that you must perform the continuity correction. So this is the first thing that you need to take note. Second thing is that in order for this approximation to be accurate, usually we would take lambda has to be greater than 15. So take note of these conditions. So now let's look at some examples. So if let's say you have x to be distributed by Poisson distribution and the lambda is 50, so use the normal distribution to approximate the following. So the first one, let's say, is P. Let's not do this. Px smaller than 50. So in this case, so I will write on the right, your normal distribution will be something like this, 50, 50. Okay. So when you turn it into the z-score, so remember the procedure. If this is less than, there's no equal, so you should use 49.5. So 49.5 minus 50 divided by the square root of 50. So if you calculate this, this is Pz smaller than minus 0.071, or you can convert it to z smaller than 0.071. So this is eventually 0.4717. So I would assume that you already know what is the procedure. So let's say you don't know the procedure. So basically, for the continuity correction, you need to look at. So let's say these are the bars. Let me draw it carefully. So let's say these are the bars. So because this is a discrete probability distribution, so 49 is over here. Sorry, I should begin with 50 and then no, here is 50, here's 49. So in order for you to avoid the number 50, you must take, so 50 is at the middle of this bar, so this particular value will be 49.5. So that's the reason for the continuity correction. So roughly the idea is that you want to avoid the number 50 for this particular case, which is why you take 49.5 for your continuity correction. And then as for how to convert all these, remember that your table in the exam always begin after 0.5. So there's no negative number. So if you encounter, let's say, minus 0.071, you have to turn it to the other side. So these are the values. Turn it to the other side, 0.071. And if you use the table, then these are the values that you will find. Okay, so in order to find the exact same value, you have to use 1 minus pz smaller than 0.071, which is over here. So these two are symmetric. So roughly that's the idea of finding the continuity correction number and how to read the table and then do the conversion and so on. So I explained for part A. For the rest of the examples, I will just write down the answer. So now if let's say you have part B, x smaller or equals to 50. So you want to include the number 50, so you have to take 50.5. So you take 50.5 minus 50 divided by the square root of 50. So if you calculate all these, you would get pz smaller or equals to 0.0707. So this is 0.5283. So if you look at p x equals to 50, so this is a bit tricky. Px equals to 50, so you would take 49.5 and 50.5. So this particular number will be in the between. So the left side, it will be 49.5 minus 50 divided by the square root of 50. So because you want to include the number 50, so this is less than or equals to z, and then less than or equals to 50.5 minus 50 divided by the square root of 50. So obviously we already calculated this value. This is minus 0.071 and then 0.071. Yep, let's do that. Let's not write that many numbers. So now this will be equals to pz smaller or equals to 0.071 minus pz smaller or equals to minus 0.071. So in the end, what you would get is 0.5283 minus 0.4717, which is 0.0566. Now part D. If you have x greater than 50, this will be pz greater than 50.5 minus 50 divided by the square root of 50. So the point here is to avoid the number 50. That's why you need to take 50.5. So we already know that this is pz greater than 0.071. So the value will be 0.4717. Now let's look at part E. Px greater or equals to 50. So this is pz greater or equals to, you want to include the number 50. So you take 49.5 minus 50 divided by the square root of 50. So this is pz greater or equals to minus 0.071. So you can turn it around to become pz smaller or equals to 0.071. So this is 0.5283. So now there are 4 sets of very tricky questions. Let's look at the first one, F. So let's say you have P 52 smaller than x smaller than 56. So this is something that you need to be slightly careful. So if we list down the possible x, so this will be x equals to 53, 54, 55. So what I would recommend you to do is to write down what are the compositions of your px in such a way that you get 53, 54 and 55. So the way, because your normal distribution table in the formula book is, so what you would read usually in your formula book is in, let's say, A is in this form. So I would recommend you to write down in this particular form so that you won't get confused. The reason why you might get confused is because of the continuity corrections. So let's look at how you would break down the left side into 2 probabilities. So the first term, obviously, if you want to write the equal sign, you will get 55. So what does this mean? This means that you have px starting from 0 up to 55. So the second term will be px smaller or equals to 52. So what does this mean? This means that you have px equals to 0 up to 52. So from up to 55 minus up to 52, you get 55, 54, 53. And this is exactly the same as the left hand side. So then at this point, it will be easier for you to break down because I already demonstrated all the 4 possibilities from A to D. Sorry, from A, B, C, D, E. So now px smaller or equals to 55. This will be z smaller or equals to. So you want to include 55, so it will be 55.5 minus 50 divided by the square root of 50 minus px, z, smaller or equals to, so you want to include 52, so it is 52.5 minus 50 divided by the square root of 50. So this will be pz smaller or equals to 0.778 minus pz smaller or equals to 0.354. So you take 7818 minus 6383, you will get 1435. Okay. So now let's look at the second case. You have 52. There's no equal sign on the left one, but there is equal sign on the right one. So this would be starting from 53 up to 56. So then what you need to do is something like this. You start from 56, you minus 52. So I won't bother to write down, to break down this part. So I will just write directly the z-score and so on. So basically the logic is the same thing, but the way I write it is such that you won't get confused if you follow exactly this particular rule of thumb. Of course, there are other ways to do it, but I personally find that if you have a very specific way of writing down the exact same equation, you won't get confused. So this is 56.5 minus 50, and then 52.5 minus 50. So you have pz smaller or equals to 0.919 minus pz smaller or equals to 354. So this is 1826. So now let's look at H. If let's say you have 56. So we know that over here this will be starting from 52 up to 55, right? So then this will be px smaller or equals to 55 minus px smaller or equals to 51. So you have, okay, you know what? I've already calculated this, so I will just directly quote the answer from above. So px smaller or equals to 55, this will be pz smaller or equals to 0.778. So the other one, 51.5. Okay, 51.5, apparently I haven't calculated it. So what I will do is something like this. this will be 51.5 minus 50 divided by the square root of 50. So this will be 0.778, 0.212. So the final answer would be this. (1978). Okay, the last one, which is I. So the last one will be both sides equal. So this will be px smaller or equals to 56 minus px smaller or equals to 51. So this will be 0.8209 minus 0.584. You will get 2369. Alright. So the reason why I did all this is so that it is easier for you to do the continuity correction. So now let's look at the conclusion for this particular section. So if you meet something like this, what you need to do when you break down into two terms, the first one has to minus 1. The second one, you don't need to minus 1. If you meet something like this, so the first one, you keep it as it is. And the second one, you also keep it as it is. If you meet the first one is equal, second one is not equal, then both has to minus 1. Lastly, if both are equal, then the first one you don't need to minus 1, but the second one you have to do it. So there you go. If you really don't understand what I was doing just now, just memorize this. Should be enough. So let's put it over here instead. Now let's look at one example. The number of tea lights that are lit at a place of memorial during the day follows a Poisson distribution the mean would be 38. So how many tea lights should be available so that you have at least 98% certainty that there are sufficient T-likes for the demand. So if you are given a question like this, the first thing that you need to do is to formulate correctly what the question actually gives you. So first thing, let's say X is the number of T likes that are lit. So we know that this is a Poisson distribution and lambda is greater than 15. So obviously you can do normal approximation. So if you approximate, your approximation will be 38. Okay. So now you need to formulate the probability. How many T-lights should be available to be at least 98% certain? So the probability by itself is something like this. There's a minimum number of lights that you need to lead up in such a way that your probability is at least 0.98. Okay, so this would be by normal distribution. So remember your continuity correction. Minus 38 divided by the square root of 38. So this has to be greater or equal to 0.98. So now we look at the normal curve. So 0.98 should be somewhere here, because the probability is greater than 0.5. Okay, so it means that when you find out what is on the right side, so pz smaller or equals to a plus 0.5 minus 38 divided by square root of 38. So this thing is 2.054. So how do you find this? You read from the table, find 0.98 and then find out what is the z-score. So this is the sort of like finding the inverse of normal distribution. So then finally a plus 0.5 minus 38 divided by the square root of 38. So this has to be greater than 2.054. So finally you find that a is greater or equals to 50.16. Take the integer, so a has to be 51. So this is the at least like minimum number of lights that you need to light up, so that it is 98% certain you have enough T lights. Okay. So the last one, which is on hypothesis testing. So the last section of this chapter is on hypothesis. Let's use the new page. Hypothesis testing with Poisson distribution. So the procedure is the same thing, but now you need to be mindful of the type of probability distribution. So previously, if you see binomial distribution, usually you are given a probability of success and failure, and then you just repeat n times. If you are given the normal distribution, then usually it will be having a mean and variance or standard deviation. So now if you are given a Poisson distribution, usually you are given the events, the average of the events over a certain period of time or a certain interval. So you need to be able to identify which type of distribution the question actually gives you. So let's look at this particular example. The number of misprint per page of a newspaper follows a Poisson distribution with mean 2 per page, following new procedures for 49 misprints are found in 32 pages of the newspaper. So the first part of the question asks you to use a suitable approximation to test at 5% significance level if the mean number of misprints has changed. Second would be how many misprints would be needed for type 1 error to have occurred. So let's look at part A. So if I let x to be the number of misprints per page of a newspaper. So originally you are given something like this, but this is per page. So now the hypothesis that you need to test is for 32 pages. So for 32 pages, your x should be 32 times 2, which is 64. So this makes use of the previous sections on trying to tell you if you are given a different interval, you convert it by ratio. So similarly over here, I convert it by ratio. So you can see that over here, lambda is greater than 15. So definitely you can use normal approximation, and you are required to use normal approximation. So the approximation would be this. So now you need to formulate your null hypothesis. Your null hypothesis should be saying that the mean remains at 64, and then your alternative hypothesis. So the questions asks if the mean has changed. It doesn't tell you whether increase or decrease. So you have to write something like this. So essentially, H1 tells you that you need to do a two-tailed test. Also, write down your significance level. It is 5%. So on the left side, you get 2.5. On the right side, you get 2.5. So now you need to test whether or not the mean has changed. So if it is a two-tailed test, you need to test from the left and from the right. See whether or not they pass the critical region. If they are not, then find out. Then basically you can accept H0. If one of it pass the critical region, then you have to reject the claim. So you find Px greater or equals to 49. You have to include 49 because in the question 49 is the number of misprints. So this is Pz greater or equals to. So if you want to include 49, you minus 1, minus 0.5. So this is Pz greater or equals to minus 1.938. So I won't bother with the conversion. Basically, this will give you 0.9737. So this particular value is greater than 0.025. So from the right, it doesn't seem like there's a problem. So now let's look at from the left. So this is smaller or equal, so you use 49.5. This will be Pz smaller or equals to minus 1.813, and this is 1 minus Pz smaller than 1.813, so is 0.0349. So this is also greater than 0.025, so therefore you accept H0. So it means that the mean does not change. So now part B. Part B asks you to find out how many misprint will be needed for type 1 error to occur. So remember what is type 1 error. Type 1 error means your hypothesis is correct, but you rejected it. So basically for type 1 error, the probability will be more or less the same as your significance level. But in this case, because you originate from a discrete random variable, so you have to find out the critical region. Okay. So your critical region, the right part, is given by this equation. So you can do like what I did just now. So basically you want to include a, so it will be a minus 0.5 minus 64 divided by the square root of 64. So over here, this will be, so because this is less than 0.5, the only way this can be true is if, let's say your a is either your a is here or your a is here, right? So what you can do instead is to change the direction of this, because right now greater or equals, so it means that, okay, for this particular scenario, your a most probably is here because of the direction of the inequality. So you change it back. So once you change it back, basically what you would have is this 1 minus 0.025, which is 0.975. So basically what I did was, okay, so a is here, so this part is, okay, it's not x, it's not z, it's x. So this portion is given by this, and it has to be smaller than 0.025. So in order for you to find this, basically you need to use from the table 1 minus px smaller or equals to a, and this has to be smaller than 0.025. Right? So you move the 1 to the right hand side and then cancel off the minus sign. So notice that the direction of your inequality has changed. This sign has changed. And finally you have 1 minus 0.025 on the right side. Okay? So now you can find out for this particular probability what is your z-score. So your z-score happens to be 1.96. So finally you find, you just move all the numbers to the right side. A is greater than 80.18 or A is 81. So your right tail A is 81. So now calculate the left tail. The left tail smaller than some number is smaller than 0.025. So then you have something like this. So you want to include the number of a, so you need to plus 0.5. So this is smaller than 0.025. So now you know that your a has to be here. So your a is negative basically. So then what you would need to do is to turn it to the other side by multiplying a minus, and this is the area that you need to find. So what you need to do is to do this. You perform 1 minus pz smaller or equals to, and then you multiply the minus sign inside the whole thing. So this is smaller than 0.025. So again, perform the same thing, move the 1 to the right hand side, and then cancel off the minus, but you need to change the inequality sign. So in the end, you have something like this. Sorry. Greater than 975. So the minus of it has to be greater than 1.96. So then a plus 0.5 minus 64 divided by the square root of 64 has to be smaller than minus 1.96. So calculate everything. A has to be smaller than 47.82, so A is 47. So these are your critical value. So how many misprint would be needed for type 1 error to have occurred? Either A equals to 47. So this is for the left tail. For the right tail would be A equals to 81. So it depends on which tail you are taking. So I think that's all for this particular chapter. Basically, hypothesis is the same thing as the first chapter. You just add it with Poisson distribution. Alright, that's all for this video. Thank you.